All right, open up your book to section 4-2. This is on page 178. The title of this section is Quadratic Functions, Factoring, and Complex Numbers. The objective is to review the properties, graphs, and techniques associated with quadratic functions. So we've reviewed these things on the previous part of this section. In particular, we've looked at quadratic functions and factoring those, and we're going to look at complex numbers in the second part. So a complex number we'll see is made up of an imaginary number. And the imaginary numbers are defined as follows. An imaginary number is a non-real number that results from taking the square root of a negative number. So we defined I as being the square root of -1. Square root of -1 is defined as I. Which means that I squared is going to be defined as -1. This is the whole reason that we introduce complex numbers, is because the fact that if I have an equation where I've got I squared or some quantity squared that's equal to a negative number, there is no value that you can plug in to give you a real solution. We have to jump to the non-real solutions. So I squared is equal to a -1. So then what exactly is a complex number? Well, a complex number then is a number that's in this form. It's in the form of a plus bi, where a is the real part and the b is the imaginary part. So it's a number that's in the form of a plus bi, where a is the real part and b is the imaginary part. Now, if b turns out to be equal to 0, then you're just talking about your real numbers. So really the real numbers are a subset of the complex numbers. As long as b is not equal to 0, then we have introduced a imaginary part to our number, and thus it's a complex number. So a plus bi. Now, just like with regular numbers, we have a number of operations that we can perform with those. And so with complex numbers, we have a set of operations that we can perform with those. Complex numbers behave just like binomial operations. So if you are trying to operate on a complex number, if you think about what you would do with a binomial, you'll find the technique is very similar. So some of the practice you've done here in the first half of this section working with binomials will be very helpful here for us. So for example, if you're trying to add or subtract, find the sum or difference of two complex numbers. The way that you do that is just the way you'd handle a binomial. If it was, 5x plus 2, and you wanted to add that to another binomial, you'd combine your x parts, you'd combine the constants, and then you can go from there. Same story here, except instead of having an x part, you've got an imaginary part. So you treat that kind of the same way you'd treat the x in a binomial. So all you do is combine the real parts, and then you combine the imaginary parts, and your answer will be written in the form of a plus bi when you get done. It's a complex number. You can also multiply complex numbers. If you want to multiply complex numbers, then you're going to use the FOIL method to get the real part. You'll get an imaginary part. That'll be the middle terms of this foiling method, the o and the I. And then the last part here will be the I squared part. So you'll get 3 terms there when you get done, just like you would if you multiplied 2 binomials together. You'd have a constant, you'd have an x term, and you'd have an x squared term. But you can do one more thing with working with complex numbers. I squared, we just said, was equal to a -1. So you can take the I squared part, replace or substitute I squared for a -1, and then simplify further. In other words, your answer will always be another complex number, because the I squared term drops out and becomes actually a real number at that point. I shouldn't say drops out, but becomes a real number when I replace I squared with -1. And we can write it in the form of a plus bi when we get done. You can also divide complex numbers. We're not going to get into that here, but it would involve multiplying by a conjugate. So let's talk about what that is. That if you want to multiply a number by its complex, or a complex number by its complex conjugate, what that means is you're taking a complex number that's in the form of a plus bi, and you're going to multiply it by a minus bi. Those are complex conjugates. You can also do this with binomials. We have conjugates of binomials. A plus bx would be the conjugate of a minus bx. You just change the sign there in the middle. The nice thing about multiplying complex conjugates together, and the same thing that's nice about multiplying binomial conjugates together, is those middle terms drop out. There's no imaginary part when we get done here, though. When you multiply the a's together, you get a squared. The middle terms, the abi and the minus abi, those cancel each other out. Realize that you'll end up with a minus b squared I squared when you get done. But I squared gets replaced with a negative 1. So when you multiply this out, you'll end up with a times a is the a squared. You'll end up with an a times bi. It's actually a minus if we do the actual foiling method there, then in that order, it's the minus that goes next. And then the plus a plus bi. And then you get a minus b squared I squared is what you actually get for the last term there. So first of all, the middle terms here cancel each other out. That's nice. Those are gone. The a squared term stays out front. And the I squared over there, that I squared is actually equal to a negative 1. So you can replace that with a negative 1. So a negative b squared times a negative 1, that turns out to be a positive b squared. So we get a plus b squared there. All right, so let's find a couple of products and sums here, I guess, of complex numbers. Take a look at example number 6 here on page 182 in your book. It says to multiply and simplify. They only say to multiply. We're going to do both here. We're going to find a sum and a product with this. So we'll do a little bit more than what they asked. But let's find 7 plus 4i. And let's add that to, let's call this part A here for the sum. Let's add that to 9 plus 10i. So again, the way that you add these together is you first combine your real parts. So I've got a 7 and a 9, so I've got 7 plus 9. And we'll add that to, and then I deal with the imaginary parts, the 10i and the 4i. So I've got 4i plus 10i. Again, just like if you had a binomial here, that's how you'd combine those. You'd combine your constants, and then you'd combine your x parts. So what do we end up with? 9 and 7 is 16 here. 4 and 10 is 14i. There is our complex number, 16 plus 14i. All right, now let's find the product. So we've got 7 plus 4i, and we're going to multiply that by 9 plus 10i. And again, the technique we use here is just like foiling. If we had binomials here to foil together, we'd do the same thing that we're going to do if it's a complex number. So you have 7 times 9 is 63. You have 7 times 10, which is 70i. I'm going to go ahead and write out all the terms here. 4i times 9 is 36i. And then finally, 4i times 10i is going to give us 40i squared. Don't forget you're squaring that i there. And now simplify this. You've got 63. You've got 70 and 36 is 106i. And the I squared, again, you can replace I squared with a negative 1. So that's really a minus 40 is what we've got sitting there at the end. And that I can combine with the 63 that's out front. So 63 minus the 40 is going to give me 23 plus 106i. There's the product of those two complex numbers. All right, take a look at example 7 here. It says to check that 2 minus 3i is a solution to the equation x squared minus 4x plus 13 equals 0. Let me write that down. X squared minus 4x plus 13 equals 0. And they want you to show that 2 minus 3i is a solution by substituting it into the left side of the equation and showing that the result does in fact equal the 0 that you got on the right. So x equals 2 minus 3i is what we're going to plug in here. All right, so let's see what happens when we do that. I'm going to replace the x here with 2 minus 3i squared minus 4 times 2 minus 3i plus 13. Now, I'm trying to show this is equal to 0, so don't write down it is equal to 0 at this point. I'm trying to show that. So let's square this thing. When we take this binomial and, this complex number and square it, which is the same as if you were multiplying two complex numbers together like we just did. So 2 times 2 is going to give me 4. And then you have a minus 6i and another minus 6i, so that'll be a minus 12i. Again, that's the middle two terms there, the o and the I and the foiling that we've combined. And then you've got a minus 3 squared times I squared. So minus 3 squared is going to be 9 times I squared. So it's going to be plus 9I squared is what we'll end up with when we square that out. And now you can distribute for the second term here. You can distribute the 4 through there. So it's a minus 8 and a plus 3i and then plus 13. All right, so let's combine all of our constants here, the real parts, I should say. So you've got a 4. Let me underline these. I've got a 4. I've got, actually, this 9i squared doesn't look like a real part, but it is, because the I squared is a negative 1, right? You've got a negative 1, or sorry, a negative 8 and a 13 here to deal with. Okay, so what do we end up with? I've got 4. I'm going to write these out. 4, and then the 9i squared, I'm going to write that as minus 9. Oops. I don't need to put that in parentheses yet. And then I've got a minus 8 and a plus 13. I'm just going to associate those together, but I'm going to replace the I squared with a negative 1. And now everything that's not underlined is the imaginary part. So you've got a negative 12i. And you've got plus 3i. Oops, I didn't multiply that together correctly, did I? Let me fix that. I got a negative 4 up here times a negative 3. That should be a positive 12i. Let me fix that there. So it should be a negative 12i plus 12i. Well, that'll give us a 0 like we're looking for, right? Hopefully this first part turns out to be 0 as well. I've got 4 minus 9 is a negative 5. Minus 8 is a negative 13 plus 13. So yeah, this is 0 plus 0i, better known as 0. Yeah, this turns out to be a solution to that quadratic equation that they gave us. All right, let's take a look at example number 8. Example A says to transform the equation y equals 3 times x minus 5 squared minus 43. So you've got yourself, this is the vertex form of that quadratic expression that's on the right. And they want us to transform this into a polynomial form, so the ax squared plus bx plus c form. All right, so that means we got to square out this binomial that we have here on the right side. So we've got y is equal to, let's first square that out. X times x is x squared. You'll have a minus 5x and another minus 5x for the middle terms there. Will give me a negative 10x. And then negative 5 times negative 5 is a positive 25. And then you got a minus 43. Don't forget you're multiplying a 3 through there on the right side. So now when we end up with 3 times x squared is 3x squared. You'll have a 3 times a negative 10, that's a negative 30x. You've got 3 times 25 is 75. And 75 minus the 43 is what? 75 minus 43 is 32. So it should be plus 32, it looks like. And there we go. There we've transformed that from the vertex form into the polynomial form. That one is not too bad. It's trying to go the other direction, that if you start with the polynomial form, can we get it into the vertex form? That actually involves a technique here that we're going to talk about next, which is completing the square. Hopefully is a term you've heard before when working with quadratic equations, or polynomials for that matter, but usually it's with quadratic. That if you want to complete the square, that is, if you want to go from the polynomial form and get it into the vertex form, then here's the steps we go through to do that. So if you start out with the quadratic expression there, x squared plus bx plus c. Notice that we're saying a is equal to 1 here for this. We'll deal with what happens if a is not 0 or not equal to 1 at the end. All right, but if it's equal to 1, then this is how we'll handle it. Or I should say we always need it to be equal to 1 here to handle it. So the technique is, first of all, to associate the x squared term and the x term. So you'll notice I put x squared and the bx in parentheses there just to indicate I'm going to handle those together. And then here's the little trick that we have to know in order to complete the square. And it requires that you take half of the linear term there, half of the x coefficient, and square it. So in our case, the x coefficient has a b there. I'm looking at this guy right here. He's a b. So if I take half of that, it would be b divided by 2. And if I square it, I'd end up with b over 2 squared. Or that turns out to be b squared over 4. That's the constant that I need to make this a perfect square. And that's the next step. We're going to add a clever form of 0. We've talked about multiplying by clever forms of 1 to be able to go from, in order to add fractions together or to convert from one set of units to another. There's lots of things we do with multiplying by clever forms of 1. Clever form of 0 means that you're adding something and then subtracting it back out. So if I take z and subtract z, that's equal to 0. You can add 0 to any equation, and it doesn't change it. Just like multiplying by 1 doesn't change anything. So we're going to add a clever form of 0 to both sides there. So in particular, it's this clever form of 0 that we just came up with from up above here. It's this b squared over 4, I guess is the way we're writing it. So here's your z, and then here's your minus z. All right, so I'm taking that form from up above, the x squared plus bx, and I'm adding z to it. And then I'm taking the c and subtracting z from that. So that gives me a clever form of 0. And what you end up with here in this first set of terms, these first 3 terms, that's a perfect square. When you have x squared plus bx plus b squared over 4, that is a perfect square. You can rewrite that as the quantity x plus b over 2 quantity squared. That right there is completing the square, which is what we've done here in this step. This guy right here turns out to be a perfect square here, and we've completed the square. And the second part of this, we just have to leave it as is, c minus b squared over 4. I guess if you wanted to, you could simplify that by getting a common denominator or things like that, but we're going to leave it in that form. One thing to note here, I guess I can show you all that. One thing to note here is I mentioned up above there that our quadratic expression that we started off with was just x squared plus bx plus c. So if there's an a out in front of that x squared term, like if it's a polynomial form there and there's a value of a that's not equal to 1, then the technique you'll use is just factor out the leading coefficient of a from each of the terms. Divide out an a from the ax squared, divide out an a from the bx, and divide out the a from the c. And then with what's left there inside of those parentheses is the same thing we just talked about up above. So you still follow the same techniques there. So just do a little bit of factoring up front before you try to complete the square. It's not that you can't complete the square with the a in there, but it definitely is more difficult. So factor that out. All right, so let's try using that technique here. Example number 9 says to write the equation y equals 5x squared plus 35x plus 17 in vertex form. So they gave it to you in polynomial form, and they want us to convert this over to vertex form, and they also say to sketch the graph when we're done. Okay, so let's first find the vertex form. That'll make this a lot easier to sketch if I know where the vertex is at, actually. So the technique that we just talked about was first associate the x squared and the x terms here. So we'll have 5x squared plus 35x. I'll put those in parentheses, plus the 7. Now you'll notice that I've got a 5 in front of my x squared. So this is kind of that note that we just mentioned on the previous slide there, that if there's a coefficient in front of that x squared that's not 1, then factor that out first. So that's what we're going to do. We're going to write this as y is equal to 5 times the quantity x squared. When I factor out a 5 from the 35, I'll be left with 7x plus 17. All right. Now I got to add in my clever form of 0, and the clever form of 0 is found by taking half of this middle term here, half of the x term. So in this case, the x term is 7x. So half of 7 is, I'm going to write it as 7 halves, I guess, 7 over 2, or 3.5. And then you square it. So that means 7 halves squared would be 49 over 4 when we square that. Okay. Take half of 7 over 2. Maybe I can just put that over on the side here just so it's clear our steps that we're doing there. I've got half of 7 over 2, and I'm squaring that. That's how I'm coming up with that constant to add. That's 49 of 7 squared over 4. That's the 2 squared. All right, so that's what I've added, and I have to subtract that quantity back out. Now, you have to be careful here when you do this, because when I subtract this out, I got to realize that I've not only added this 49 over 4, but I'm also going to be multiplying that by the 5 that's out front. This 5 out front is actually getting multiplied by that 49 over 4. So it's not just a 49 over 4 that I got to subtract out of this thing. All right, it's 5 times that quantity that I've got to take into account. So we got to subtract out, I'm going to write it that way, 5 times 49 over 4. All right, so now, turns out this first part is now a perfect square, which was our whole purpose of doing this problem, was to complete the square here. So what do we end up with? We got 5 times, well, to rewrite this, I'm going to write this as x plus some quantity, and the quantity turns out to be the square root of that last part there, that 49 over 4. Square root of 49 over 4 is 7 halves, or 3.5, however you want to write that. You can double check that though. Double check that when you square that out, you're going to get what we have up above there. And then we're going to add on this 17 minus 5 over times the 49 over 4. I'm going to grab the number they give us in the book there, but you should punch that into your calculator and verify that. Looks like that turns out to be 44 1/4 that we're subtracting off here. Minus 44.25. All right, so there we go. We've got it in vertex form. A times x minus h squared plus k. You might want to rewrite that just so that it's actually looks more like that form, so you don't mess up your h and your k. If you write it as x minus, it's x minus the h value. So I'm going to write this as x minus, maybe I'll write it as a negative 3.5 instead of 7 halves. It's fine either way though. Squared. And then plus k is how we're supposed to write it, so plus, it would be the opposite of 44.25. Again, if you write it in that form, that just might help you see what the hk is, and so you can see the actual location of your vertex. My vertex then is this right here. Here's my h, this is my k. All right, so the second part of this was to then graph this. Well, now that I know where the vertex is, I can sketch that pretty easy here, actually. Actually, we'll come up with a couple more points to plot here to help us sketch this, but let's draw this way. Let's go. So my vertex is at negative 3, negative 44. Okay, so I'm going to make this go by tens here. So 10, 20, 30, 40, 50. So this will be negative 50. And if we just go by ones here on our x-axis, 1, 2, 3, 4, 5, 6, 7, we'll say. This is negative 7. 1, 2, 3. This is negative 3. There's negative 4. Okay, so I can plot the location of the vertex here. The vertex was at negative 3.5 and then down in negative 44.25. So that's somewhere about right here, almost halfway between negative 40 and negative 50 down there. So there's the location of my vertex. In fact, I'll mark that, negative 3.5, comma, negative 44.25. And actually, if I go back to the original form, I can get the y-intercept real easy. The y-intercept is just the c value here, right? If I plugged in x equals 0, you'd end up with just 17. So we're going to cross the y-axis at 17. So let's mark that as well. Let's go up by 10s here. There's 10, 20, 30. So this is 20, this is 10. So I can plot that point. So 17 is about right here, we'll say. And actually, there's symmetry about this vertex, right? If you drew a dashed line right through the vertex at -3, there's symmetry here. So if I go 3.5 units to the right, that's where I found this x-intercept. If I go 3.5 units to the left, I should find another point over here. So at -7, I should also be up at 17 then is where that should be. So I actually got 3 points here plotted. I can come up with a pretty good sketch of what this thing must look like. Let's do something like this here. Okay. All right, and that's the end of the section 4-2.